You are all welcome to Chemtech. So, like we said, we are going to do live today again on this same topic to finish up the energy. Just let me know you are available. Send a message, make a comment that you are around to, to enable me know that you are around. Please do that. Okay. Please, we are waiting for more response. More response. We are waiting for more response. So we are still waiting for more response. We are waiting for more people to come online.
That's a board bend.
So we are still waiting for more persons to join us. The orientation is, is it okay? While we are waiting for more persons to join, by 10:30 we will start. The topic we are doing today is energy associated with nuclear chemistry. Energy associated with nuclear chemistry. Since the stuff is not properly fixed.
But this thing is too late. That's what I'm surprised.
We are waiting for more persons to join. So I hope it's clear. Everyone can see. So we are waiting for more response. Meanwhile, so are we there? Okay. Please, I want you to keep us sending I to so that I can know that you are present. If you can see, let me know that you can see it. So we are looking at for energy associated with nuclear chemistry. Nuclear chemistry. So in our previous video, in our previous live video, we looked at the nuclear reactions, stability of a radioactive compound, how you know an atom is radioactive and or elements are radioactive. So we looked at that and we were able to differentiate the types of radiations that we have. There are particles, the particles that are accompanied by these radiations. We talked about the alpha, we talked about the beta particles, and we talked about the gamma particles. So we are doing a pre-review because of those that are just joining. We are doing pre-review of our last live video on nuclear chemistry. So we have gone far. We have talked about natural and artificial radiations, and we said natural ones are the ones that occur naturally without any without any bombardment with energy. But artificial radiations are the ones that occur by bombarding elements with high energy particles, like the gamma, like I said. So those ones will now make an atom to undergo radiations. So we can bombard particles with neutron, with deuterium, with proton, you know. So that is it. Then we also try to balance nuclear reactions. Now we want to talk about the energy associated with nuclear reactions. Are we okay? Can we see? And with this energy, for us to understand the energy associated with nuclear chemistry, we need to know nuclear fusion, what nuclear fusion and fusion, fission are. So when we talk about nuclear fusion, we are talking about bringing two particles or two radioactive particles together to form a larger nuclide. You know, nucleo will come together. Let's say nucleo plus another nucleo. I told you that a nucleo is a particle that is present in a nucleus. Are you seeing it? So in a nucleus we have what they call proton and we have what they call neutrons. So the two combined is called nucleus. That is NucLeons. So it's the combination of proton plus neutron will give us nucleus as particles. So when we have these two coming together, they will form a larger nuclide. They will form what? A larger nuclide. For example, we are talking about fusion. Don't forget, we are talking about fusion. For example, helium and proton particles. We know proton particle has a mass number of 1, atomic number of what? 1, plus another proton particle. Are you seeing it now? So if these two come together, with the help of energy, it will give us a larger nuclide. Are you seeing it? A larger nuclide like 2He. What atomic number is this? We have it as E. Then we have what? 2. Or we can say we have 2, which is an isotope of what? Helium. Or we can also say a proton combining with a deuterium. What is a deuterium? A deuterium is an isotope of hydrogen. Are you seeing it? A deuterium is spelled Deuterium. Deuterium is an isotope of what? Hydrogen. Remember in our previous live video, we said an isotope is any atom that has the same atomic number but different mass number. So that is why we say proton. The isotopes of protons are deuterium because it's heavier than a proton. So it also retains the atomic number of 1. Maybe we still have tritium. Tritium is when the hydrogen itself has a mass number of 3. So it is also represented as T, but 1. The atomic number there will be what? 1. All these are isotopes of hydrogen. Imagine all the isotopes of hydrogen coming together. We now call it what? Fusion. And this coming together is because there is energy. Energy is absorbed for it to come together. So if you add up together, we will have 3. And what is the atomic number of 3? 3 is lithium. So when you add all the mass number together, we have 1, 2, that is 6. So you see that we have an isotope of what? Lithium, that becomes a radioactive particle and it becomes a nuclide. So coming together of two small nucleus or 2 small radioactive particles to form a larger nuclide with the help of energy. So that is an example of fusion. You see, in our daily life, where do we experience nuclear fusion? The sun. The sun is composed of 73% hydrogen, 26% helium, and 1% every other element. That's what makes the sun. That is what forms the sun. So the sun is an example of nuclear fusion. The fusion of hydrogen particles, helium particles, and 1% of every other element in the world, according to the spectroscopic study of the sun. Are you seeing it now? So when energy is released, the sun is being what? Formed. That is what? Nuclear fusion. Then nuclear fission, when we talk about fission, we are talking about bombardment of a larger particle with energy to form smaller what? Particle. To form smaller particle. That is fusion. So I want to see the comment section. Are we together? Are we together on the comment section? Forming of smaller particles is called fission. But for fission is what? The larger particle is formed into 2 smaller nuclide with the release of energy. So I'm going to give example of the fission. So let's not confuse ourselves. We are going to give example of the fission. The first one, we talked about fusion. So I will leave fusion on the board for those that are joining us late so that they will understand what fusion means. Fusion means this, means 2 nucleus or two smaller nuclei coming together to form a larger with the help of energy. Let me write it properly. With the help of energy, we use example of proton, plus what? Another, this proton with mass number of 1. Then the isotopes of proton is deuterium. When you add them together, you will have a larger one, which is what? The larger one, which is what? Helium. So you see, this is an example of fusion coming together of two with the help of an energy. The energy here is the neutron to give us what? Helium particle. Now for that of fission, fission is a larger nuclide, is bombarded with a lot of energy to give us smaller nuclide. Like the examples we have been giving in the previous video of life, we said that uranium is 23892. Now when you bombard this uranium with neutron is high photo energy, just like gamma. You can bombard it with gamma, you can bombard it with what? X-ray. So whatever energy, you can decide to put it as energy. So now this larger nuclide is now bombarded with energy to give us smaller nuclide, like 2 3, let's say 2 3 4 thorium we know is 90 plus what? 42He. Are you seeing it? So this bombardment can be of different form. It can give us the titanium, which is,
Okay.
you can give us the lithium, which has atomic number of let's say 90. No, I don't think it's 90 something, 85 or so. Then continuous, it will give us other what? Particles. So when a large nuclide is bombarded with energy, will give us smaller nuclide. Smaller what? Nuclide. So that is nuclear fusion and fission. So what is the difference between them, the similarities or the difference between them? In similarities, it occur with nuclear particles. That is the similarities of them. Are we together? Hope we are together, we are listening. uh is there any question at the comment section? Are we on the same page? Okay. So the similarities of nuclear fission and fission is that it has to do with nuclear particles. It has to do with nuclear particles. And energy is associated to both. Energy is associated to both nuclear fission and nuclear fission. But what is the difference? The difference is that in fusion, two smaller nuclide combines to form a larger nuclide. For example, we have the sun. Formation of the sun is from the smaller particles of hydrogen and helium with every other element to give us sun. But for fission, fission is larger particles. Larger particle will disintegrate. When bombarded with energy, it will disintegrate to form two smaller particles. And with this, we have experience with nuclear bomb. You see, when they lit up the nuclear reactor, what happens? It goes up and what? Distributes its energy. Are you seeing it now? So example is atomic bomb. If you want to make atomic bomb, you find a larger particle that has that ability to disintegrate to form a smaller what? Particle. So that is how bombs are made. That is how bombs are made. More also, uranium as a particle has the ability to make a nuclear bomb. It has the ability to make, in short, it is known for its, because of its energy. It can give us, if we decide to what, power the whole nation, we can use uranium energy to power the whole nation. You can use it for energy. Are you seeing it? So because of the large property of uranium, uranium has the atomic number of 92 and mass number of 238, and it can disintegrate to its isotopes. Isotopes of uranium can be that with 234, 235. We have uranium 234, we have uranium 235, and we have uranium 238. But the one that is specially used for making bombs are the one with, is the uranium of 235. That is the common one. So that is that for nuclear fusion and fission. So our understanding on this nuclear fusion and fission will now give rise to the energy associated with nuclear chemistry. The energy associated with nuclear chemistry. I don't know if I can think the word. I will go through the comment section to see what we are saying. So, like someone said, I should come again with deuterium. Deuterium is an isotope. Deuterium is an isotope of hydrogen. And it's represented with D. Deuterium is an isotope of what? Hydrogen. It's also called an heavy hydrogen or an heavy proton. What is the difference between hydrogen and deuterium? Hydrogen has a mass number of 1, but deuterium is having a mass number of 2, showing that it's heavier than what? Hydrogen. Are you seeing it now? So that is deuterium. We also have tritium. Tritium is when the hydrogen is having a mass number of what? 3. Are you seeing it? So they are all isotopes of what? Hydrogen. Now, we will now go direct to the energy associated with nuclear chemistry. You see, the energy associated with nuclear chemistry was actually the energy of Albert Einstein. Albert Einstein said energy is directly proportional to mass. Are you seeing it? Is directly proportional to mass. That means if you increase the mass of a substance, the energy will also what? Increase. So it is that same energy that we use in relating the bombardment of nuclear particles to form larger, or combination of nuclear particles to form larger, or disintegration of larger particles to form what? Smaller particles of a nuclide. Now, this mass is what is associated to what? To nuclear particles or nuclide. So the energy is equal to mass times what? The speed of light. Mass times the what? Speed of light. Meaning that for every particle, for every mass of a particle, the energy will what? Increase. For every mass of a particle, of a nuclear particle, the energy will what? Increase. Why will it increase? Because of what? The speed of light. No matter how small the mass of the nuclear particle is, the energy also will be high because of what? This speed of light. And this speed of light has a large value of 3.0 times 10 raised to power 8 meter per second. So c square is equal to what? 3.0 times 10 raised to power 8 meter per second. That is the time taken for a particle to travel as far as possible. That is speed of light. So if you are saying c square, it means that value will be 3.8 times 10 raised to power 8 raised to power square. That means c square will be 9.0, because a value of 1c is equal to this. Then c square will be equal to 9.0 times 10 raised to power what? 16 meter per seconds. So that is how the speed of light helps to increase the mass of a radioactive particle to give us high energy. Now, what is this mass? Now, for mass of a substance is quite different from a particle. It's quite different from a particle. And the mass that is measured in a particle is measured as atomic mass unit. Atomic mass unit. And we know one atomic mass unit one atomic mass unit is equals to 1 over your Avogadro's number. And what is your Avogadro's number? That is 1 over 6.02 times 10 raised to power what? 23 particle. That is for Avogadro's number. So if you divide it, you see that 1 AMU means atomic mass unit. One atomic mass unit will be equal to what? 1.6 times 10 raised to power what? 24 gram. 1.6 times 10 raised to power 24 gram. So that is for the mass. 1 AMU is equal to 1.6 times 10 raised to power 24 what? Gram. So this raised to power 23, when it goes up, it becomes minus. It becomes minus. So it's 1.6 times 10 raised to power minus 24 what? Gram. Minus 24 gram. Now this energy becomes a change in what? Energy. To know the total energy a nuclear reactor will possess, it will be what? Change in energy. Energy that it uses to start up a reaction, and energy that it releases afterwards the reaction. So if the energy is a minus sign, you know that reaction is exothermic. So for a reaction to be exothermic, if nuclear fusion has what occur? Nuclear fission as in larger nuclide disintegrating into what? Smaller particle. So it will release what? Energy. Nuclear fission has occurred. But when the energy becomes a positive energy, you know that nuclear fusion means that two particles coming together to form what? Large particle. Now the change in energy becomes change in mass, mc square. So this energy will now be equal to mc square delta m. And what is that delta m? The delta m is the mass of the product minus mass of the what? Reactant. That is change in mass of the product minus change in mass of the reactant. So we don't use, because for every substance, one substance is what? One substance is the mass. Are you seeing it? For every one substance, according to Albert Einstein, the mass is talking about is the body. But when we now relate those mass to smaller particles, we begin to see that we have to include both the mass of the reactant and also include mass of the product to know the total mass of that reaction. So that is why we have it as delta M, mass defect, which is mass of the product minus mass of the reactant. So now that we know the energy associated with nuclear chemistry, let us see how we can apply this energy to nuclear reactions. And these nuclear reactions, like I said, can be nuclear fission or nuclear fusion. So as of that, let's see how we can go with the next slide. So are we there? Okay. So please let us see if we can continue. If we can continue. Energy is equals to mc square delta n. So for example, so you can take this example down. For example, calculate the energy calculate the energy no Esther is asking if we should write note or you give us no. Please, I'm not going back to this topic again. This is where you get your notes. This is where you do whatever you get the understanding of the topic. This is the best time to get the understanding of the topic. I'm not going to class again to repeat this subject. Thank you. Thank you. So let's continue. So we have done that of energy. We have shown how energy can be calculated in nuclear chemistry. Now, the next thing to do before we take an example, we will look at the nuclear binding energy. The nuclear binding energy. What is nuclear binding energy? Nuclear binding energy is the energy required to separate a nucleus into its individual nuclei. Energy required to separate a nucleus into its individual nucleus. So what are we saying? We are saying that the energy associated with nuclear chemistry from Albert Einstein, I'm sorry, excuse me, let me get something to clean the board properly. So the binding energy, I said, is the energy required or the energy released, either you say released or what required for a nucleus to be what separated into its what component, so that you don't need to into its component. Like I told you, I said a nucleus, a nucleus is the center of the atom, and this nucleus contains what? It contains proton and what? Neutron. Contains proton and neutron. So the combination of these two, proton and neutron, are the particles of what? Nucleus. It is now called nucleus. Nucleus. So that is the name. A nucleus are what? The particles of proton and particles of what? Neutron. They form what? The nucleus. They form the nucleus. So binding energy is the energy required to make nucleus to be separated into its components. Its components are what? Proton and neutron, or to be separated into its nucleus. Are you seeing it? So means that how do we now calculate the binding energy? We now said the binding energy is from the E is equals to mc square, which I later told you that this energy, the mass here is the mass defect, which is predicted mass minus what? The actual mass. Sorry, the actual mass minus the predicted mass will give us the mass defect. E can also be the mass of the product minus the mass of the reactant. So you don't get confused depending on how the question look like. If the question is after the mass of the product or the mass of the neutron or the reactant, then you know that the mass defect will be calculated as what? Mass of the product minus mass of the. But if the question is the particles that are involved, you should calculate the particles, the energy of those particles that are involved. That means the mass defect here will be what? The actual mass of the neutron minus the what? Predicted mass. And those values of the actual masses of both proton, neutron will always be given to you, will always be given to you. But in an ideal sense, you will need to know the mass of an electron and the mass of a proton. And we know that from the previous live video, we said the mass of an electron is always 9.11 times 10 raised to power minus 28 gram, and mass of proton is always 6.4 times 10 raised to power minus 24 gram. And this is something that spectroscopic studies have already been giving. They've already used it to predict those masses. So, but the mass of a nucleus, the actual mass of a nucleus is always 4 points of an helium, sorry, not nucleus, of an helium particle is always 4.00150 AMU. Remember I told you that in nuclear chemistry, it is the atom, the particles that is involved. So that is why the mass is usually the mass of that atom. So the mass of helium atom is ANU. So it is atomic mass units of that helium. So now it means that if I want to get the mass of this helium in gram or in kilogram, I will now use the formula that I told you, that mass is equals to 1 over Avogadro value, and that is 1.6 times 10 raised to power minus 24. So if I'm to convert this, 1 AMU is equals to 1.6, 1 AMU is equals to 1.6 times 10 raised to power minus 24 gram. How many will be 4.00150 AMU? So it will be this times this that will give us the actual mass of what? Actual mass of helium in gram. In gram. And if you are to do it in kilogram, you know it's what? You divide by what? 1000. Gram to kilogram, you divide by 1000. So it means if I divide this by 1000, my raised to power 0 will reduce to 21. Are you seeing it? To 21. So it's either in gram or in kilogram, but atom mass is always measured in what? U. So let's continue. So we will now take an example of how to illustrate your predicted mass and your binding energy, on how to associate them. We know that the binding energy is the energy required for a nucleus to be separated into its what? Nucleus. And the nucleus include what? Proton and neutron. The nucleus include proton and neutron. So let's take example. So let's take the example. For example, the actual mass of calculate calculate the binding energy. Calculate the binding energy that is associated with the nuclear. Are we there? Calculate the binding energy that is associated with the nuclear fusion reaction calculates the nuclear binding energy that is associated with the nuclear fission the nuclear fission of an helium particle. If the actual mass if the actual mass of the nucleus if the actual mass of helium is given as if the actual mass of helium is given as 4.00150 AMU, and that of proton and neutron are given as 1.00 given as 1.00728 and 1.00866 AMU respectively. In the reaction below in the reaction below in the reaction below so I think we should write the question, then we will now look at the reaction below. So let's look at the question, then later we'll write the reaction below, because I need to clean the board for us to write the reaction below. So while we are waiting for others, let me go through the comment section. While we are waiting for you to be through with the question, I'll go through the comment section. Okay, Victory Maboy said, I don't understand. What don't you understand? You need to let us know the part you don't understand. Victory Emmanuel, you need to let us know the part you don't understand. Are you just joining us? So Victory, we are waiting for you. Are you just joining us? Let's know the part you don't understand. Okay. Victory, you said the part you just finished explaining. Okay, which is energy, nuclear binding energy. Okay. Is Magnificent is asking, is the nuclear binding energy the joining of neutron and proton? Yes, yes. The energy required, it is not just the joining, energy required for nuclear fusion or fusion to occur. That is the binding energy. So when we say binding energy, we are talking about the energy release when the energy release or required to separate a nucleus into its individual nucleus. That is the difference between a more stable particle and its components. So Emmanuel, we are saying that binding energy, just like the energy of Albert Einstein, is the energy required for a nucleus to be separated into its components. For a nucleus to be separated into its components, and its components are the combination of neutron and proton. Its components are the separation, are the combination of neutron and proton. You know, when we, an atom contains a nucleus, and that nucleus, we said it has two particles, proton and neutron. So for we to separate the nucleus into its proton and neutron is what we need, the binding energy, is what we call the binding energy. That energy that is required for that operation to occur is called the binding energy. So are we good to go, Emmanuel? Magnificent. I think you understand what I'm saying. So we can continue. So have we written the question? So if we are there, let me know. If we are there, let me know by just sending I. Okay, thank you. Thank you. We need more eyes. We need more eyes. Joy, thank you. We need more eyes. Okay, thank you. Uma, thank you. We need more. We need more. Thank you. Magnificent, thank you. Okay, Eunice, thank you. We need more, 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 please, so that we can continue with the calculation. If you are done with the question, just let me know by sending I. Okay, Faith Aruna, thank you. Uma, noted. So let's now continue by taking the reaction below. So I said in the reaction below. So what is the reaction? The reaction is that, what it simply means is that the reaction below simply means that energy plus helium will give us what? Proton. We said we only have proton from the question, we only have proton and neutron. So proton is H11 plus neutron. Neutron is zero, 0. And so let's balance it. We balance it. There are two here, but here is just 4. So it means if we put 2 in front of proton and we also put 2 in front of neutron, so it means that, yeah, when we bombard helium particle, we will get two hydrogen particles and 2 neutron particles. So that is 2 times 1 will give us 2. 2 plus this 2 here equals to 4. 2 times 1 will give us 2. 2 times 0 is 0. So 2 plus 0 will give us 2. So the reaction is balanced. So the first thing is to balance the nuclear reaction. That is the first step is to balance the nuclear reaction. So now you look at it, the reaction is what? Balance. But now they gave us the actual mass of helium. Actual mass of helium, they said is what? For mass of helium, actual mass of helium is equals to 4.00150. Then mass of proton was also given to us, and mass of neutron was given to us. Then mass of proton is equals to what? 1.00728. This is AMU. Then mass of neutron was also given to us. Mass of neutron is equals to 1.00866 AMU. So the masses were given to us. So and remember that it's the energy we are calculating. So what is the energy? The energy is E equals to delta NC square. E, that is the energy we are calculating, the binding energy. E is equals to MC what? Square. So, and we know that our N is delta what? N, mass defect. And we know that mass defect is actual mass minus predicted mass. Actual mass minus what? Predicted mass. Or we say what? Mass of the product minus mass of the reactant. So either we say mass of the product or minus mass of the reactant. Or we say predicted mass minus what? Actual mass. So whichever one you decide to use, you will have the same, you should have the same what? Value. So whichever one you decide to use. So mass defect is equals to what? Predicted mass minus what? Actual mass. Or we can say mass of the product, mass of the product minus mass of the reactant minus mass of the reactant. So whichever way you do it. So that is delta N. So it means we will need to calculate delta N before we can get the binding energy. So what is, we'll take it one after the other. Helium. How many particles of helium do we have? We just have one particle of helium. But for proton we have two, and for neutron we have what? Two. So if the mass of one proton is 1.00728, that means if we are having two, that means this will be times what? 2. The mass of proton will become times 2. The mass of neutron will also become times what? 2. Because one mass is 1 point. So 2 mass will be 2 times from the reaction. So we will get our calculator, know the mass of the proton. Know the mass of the proton. Let's calculate that together. Two times 1.00728 will be equals to what? 2.00728 zero 728. So times 2 is equals to 2.01456 AMU. And the other, mass of neutron. For mass of neutron, you also do the same thing. 866 times 2 will be equals to 2.01732 AMU. So you see, we have gotten the mass based on the what reaction for proton and neutron. Now we will now get our mass defect. What is the mass defect? The mass defect is predicted mass minus the actual mass. Predicted mass minus the actual mass, or mass of products minus mass of what? Reactants. So in this case, we are going to do it as mass of products minus mass of reactants. Delta M will be equals to, so these are products and these are reactants. So it means you will now add the two together. You will add both mass of proton and mass of neutron, which is 2.01732 plus 2.01456. That will give us 4.03188. That is mass of product. Then the reactant is helium, which is 4.00150 AMU. Is that not it? So you will not do it in your calculator. Press your calculator. Know the difference as 150. That will give us what? Our mass defect is equals to 0 point what? 03038 of an helium. The actual mass of an helium, so I think that is the value we have, AMU. If you press your calculator, you have that as AMU. So the mass is 0.03038 AMU. So now that you have calculated the mass, the next thing is to now calculate the energy. And we know that the unit of energy is measured in joules, and joules is equals to 1 kilogram. Joules is equals to 1 kilogram meter square per second square. That is the unit of joules. So if joules is 1 kilogram meter square per second square, meaning that this your mass cannot be in AMU. Means that your mass cannot be in what? AMU. You need to convert that your mass to what? Kilogram. You need to convert your mass to kilogram. In converting this mass to kilogram, it means you will now multiply this value. You know, I told you 1 AMU is equals to 1.6 times 10 raised to power minus 24 grams. So if it's in kilogram, you divide it by 1000. So if 1 AMU is equals to this, that means this one will now be what? This times 1.6 times 10 raised to power minus what? 24 gram. That is in gram. When you have done that, you will now divide the answer by 1000. You divide the answer by 1000, you know you have gotten it in kilogram. So let's do that with our calculator. Times 1.6
Minus 27.
That's in kilo now. So let's press our calculator. Mm.
Okay.
Okay. So let me press my calculator now. You will have 4 points. You have 4.86. 4.86. If you do that, you have 4.86 as the max. 4.86 times 10 raised to power minus 29. You have 4.86 times 10 raised to power minus. So I think I can clean the board now to start from here. So your delta M, when you do that, your delta M will be what? This 1.67. Sorry, 1.67. So your delta M will be what? 4.86 times 10 raised to power minus 27. That is your delta M. So now you have gotten delta M. Put your delta M in MC square. MC square. So you know that C square is what? Speed of light. So that means we have 4.86 times 10 raised to power minus 27 gram. Sorry, this is in kilogram, not in gram, in kilogram, because you divide this whole by 1000. So you divide it by 1000, this will increase to 27 kilogram uh, times 3.0 times 10 raised to power 8 square. So what do you have? Put all those values together. What do you have in joules? What do you have in joules?
I'm sure that's the one.
Please, I showed you people how to press calculator so that we don't have different value. Ensure you use board mass before you press your calculator so that it will be easier for you to understand. So you will have 4.4. 4.4. So everybody, are we together? So what do you have as your answer? 4.4 times 10 raised to power minus 11. Sorry, 4.54 times 10 raised to power minus 11 joules. So press your calculator and let's see what you have from the values given to you. So I'm going through your comments. Let me see. Please let me see your comments. 4.86. Okay. Okay, 4.4. Some person say 4.4. No, you can't get raised to power minus 29. Go through it again. Your raised to power minus 29 is not correct. It is minus 27. If it is the mass you are talking about, Eunice, hope you are with me. If it's the mass you are talking about, it's not minus 29, because 24 is the is in gram. Then if you are saying it's in kilogram, it will be minus 27, because you are dividing by 1000. Minus 27. So extra oyibo, you are saying that your own is raised to power minus, is supposed to be raised to power 26. No, it cannot be raised to power 26. It is raised to power minus. You have to multiply 0.03038 times 1.67. Do it times 1.67 times 10 raised to power minus 27. Do that again, please. You cannot get raised to power 26. Good. Minus. Okay, if you are saying minus 26, you are okay, you are good to go. Maybe you over approximated. If you say it's minus 26, you are good to go. Okay.
No, no, no. Minus 27.
That is for the mass, right? Yes. AMU, is AMU also gram? No, AMU is not gram. AMU is atomic mass unit of one atom, but gram is weight of a substance. So you will need to convert AMU to gram, and in converting AMU to gram, one AMU is equal to 1.67 times 10 raised to power minus 24 gram, but energy is measured in kilogram, so it will be 1.67 times 10 raised to power minus 27 kilogram. Minus 27 kilogram. Okay. Joanne said he had minus 26. You are right. So Joy, hope you understand what you are saying. Okay, thank you. Thank you, Joy. Thank you, Joy. So it means we can continue. So when you get minus 26, you have to press your calculator again. And let me press my own again and be sure. So we have 0.03038 times 1. Please always put your brackets so that you don't get confused, because calculator sometimes can give us wrong value if we don't put it in board mass, if we don't apply board mass to it. Okay, I'll press my calculator. It's minus 29. It's minus 29. 5.0. So the actual value of mass is 5.07346 times 10 raised to power minus 29 kilogram. So minus 29 is correct. Minus 29 kilogram. Then apply board mass again to it. 3.9.0 times 10 raised to power minus 10 raised to power 16. So you will have 4.67 7 times 10 raised to power minus 12. Okay, thank you. Please take that correction. Take the correction. Let me go through your comment and see those on the right track. Yes. Joanne, what don't you understand? How did you that value in brackets? Okay. What I mean by putting value in bracket, I mean do it in your calculator. Press your calculator. When you are pressing your calculator, ensure that you put them in bracket so that you will get the right answer. You will get the right answer. That is a job. Put your calculator in bracket so that you can apply board mass on its own automatically. um Don't just press it direct, you may get wrong answer like that. Okay, why did I put bracket there? You know our speed of light, mc square. Mc square, our mc square is speed of light, and the speed of light is mc square. That is 3.0 times 10 raised to power 8 square. That's the meaning of the bracket there. So I'm going through the comment section. Make your correction. That is how we got it. Joanne, I don't understand. Hope you now understand now. Okay, thank you. Oyibo, you are correct. Ma, how is it 5.073? Multiply it by 1.67 times 10 raised to power minus 27. Your AMU is multiplied by 1.67 times 10 raised to power minus 27, please. Good. Is it 26 you had? Please multiply it properly. If you have 26, put it in kilogram. Are you seeing it? Because joules is measured in kilogram. So for Ale Iwogo, I can't pronounce your name, sorry, but you know what I'm saying. The person that commented on 0.03038 AMU is equal to 5.07 times 10 raised to power minus 26. You are correct, but that is in gram. If you now convert it to kilogram, converting this value to kilogram, you divide by 1000, you get raised to power minus 29. Because energy is measured in kilogram meter square per second square. No, it's not 4.6. Esther, it is not 4.86 because we made mistake of the value. It is 1.67 times 10 raised to power minus 24, not 1.6 times 10 raised to power minus 24. Good. Iwo, you are very correct. You are correct now. You are correct now. Joy, you are correct. Very correct. Yes. That is the final answer, Joy. Iwo, that is the answer for the maths. You are correct now. So I need more comments. Ogo. You are correct, Ogome. Ogo. Okay, Esther, yeah, you have to take it gently. The mass, the one mass of AMU, one AMU is equal to 1.67 times 10 raised to power minus 24. So your answer, which is 0.0303838, will now be equal to what? So it will now be 0.03038 AMU times 1.67 times 10 raised to power minus 27. That will give us the mass in gram. But because energy is measured in kilogram, you will now divide that mass, that value that you have gotten, by 1000. If you divide the value by 1000, you will get your mass defect, which is your change in mass, to be 5.07 346 times 10 raised to power minus 29 kilogram. You will now get your answer in kilogram. After doing that, the mass that you have gotten, you will use it to calculate for energy. The energy is equal to change in mass times speed of light, and your speed of light is 3.0 times 10 raised to power 8, and you know it's mc square, so it will be 3.0 times 10 raised to power 8 raised to power square, and that will give us 4.56 or 4.57 times 10 raised to power minus 12 joules.
Okay. So that's good.
24 is a gram. So do we understand it now? Okay, thank you. Glory said he's just joining. Sorry that you are just joining. Please, next time try to join early so that you will follow up. But you can go through the video from the beginning on your own later, after the live video. Okay, Joan said we should explain how we get 5.0. I just said that now. How we got 5.0 is um 0.30 is on the board. 0.03038 times 1.67 times 10 raised to power minus 24. Minus 24 is on your is there on the board. So that is how to calculate energy. That is how to calculate binding energy, and that is the binding energy that we said is associated with what? Nuclear chemistry. Then we said half-life and radioactive decay. What is half-life? The next topic now is half-life and radioactive decay. What is half-life? We already know that half-life of a radioactive element is the time taken for half of the total number of atom in a given sample of element to what? Decay. So it is the time taken for radioactive spaceship that is present to lose half of its what? Radioactivity. Just like we did our first order of reaction. We have first order, second order, third order, and we know that the formula for first order is saying that the concentration of the reactant is raised to power what? 1. But for that is for chemical reactions. It's also the same for radioactive elements, where we now say that the number of elements at time t, the number of atoms at time t So that is energy. I think I can clean the board now. So this half life of a, we will do example, we will do other example on the energy, but we just want to quickly talk about the half life so that we take both energy and half life examples together. Hmm? So half life of a radioactive element is what? The number of molecules reduces by what? Half. So this is the reaction of the half life. So if the number of molecules is reduced, sorry, the number of atom, I'll keep using molecules, but just know that it's atom I'm talking about. So if the number of atom, this is the relationship for a first order reaction. You can remember that this is the relationship for first order. You can go through our previous video where we talked about chemical reaction, first order, second order, zero order. So in following that order of reaction for a radioactive element, we now say that Nt will be equal to 1 all over 2 the original. Is that not it? At times 0. So that means we have it, introduce our natural logarithm, don't forget the formula, 1 all over 2 NO all over what? NO equals to E minus delta T. Why do we say over NO? We are bringing like terms together. We need to bring like terms together. So introduce your natural logarithm, then you will have it as what? This one will cancel this. Is that not it? And we have it as what? The 1 all over 2 is equals to E exponential lambda T. Is that not it? So in this case now, we know that when we introduce natural logarithm to both sides, exponential will go. Is that not what we said? Exponential will go. So that means minus lambda what? T. So what is the natural logarithm of 1 over 2? Meaning if you use simplified mathematical method, we have the 1 minus what? The 2 equals to minus lambda T. Is that not it? And the 1 is equals to 0. The 2 is what? 0.693 equals to minus lambda what? T. So that means our lambda, which is represented as what? As radioactive decay, is equals to what? 0.693 all over half life. Your T is half life. Remember, we are talking about radioactive decay. So making half life subject of the formula, we have half life is equals to 0.693 all over lambda. So that is how to calculate the half-life of a radioactive compound. And it's also what? It's always on first order reaction. So we cannot take example on both energy and first and the half-life of a radioactive element. So can we continue on the example now? You say you cannot see. It's very clear now. It's very clear. Okay, let me rewrite it so that we see it very well. So let's look at it together. I said half life of radioactivity. So when we talk about half life, we said is the time taken for half of the number of atoms involved in the radiations or in radioactivity to be reduced by what? Half. To be reduced by half. That is what? Half life of a radioactive element. Now, how do we present it? A number of atoms at time t, number of atoms at time t is equals to the initial the initial number of atom e exponential standard lambda t. Are you seeing it? So this is the formula we know from our previous video where we talk about chemical reaction, first order reaction. We said that the 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 reaction, the rate of reaction depends on what? The initial concentration. The same thing is applicable to nuclear reactions. So for nuclear reaction following this first order, is that number of atom at time t is equals to the initial amount of the atoms times the exponential lambda t, where t is the time taking, and is measured in what? Is the time taking for the radiation to occur, and is measured in seconds. Is measured in seconds. While lambda in this case now is the radiation radioactive what? Decay. Radioactive decay. That is lambda. The number of disintegration. So mt now is equals to what? The number of atom, the number of that what? That disintegrate at time t, that disintegrate at time t, at time t. While n zero is the number of atom that disintegrate at time what? Zero. At time zero. That is n zero. N0. So how do we prove the half-life of this reaction? In proving the half-life of this reaction, we simply say n at time t, n at time t will now be equals to half of the initial concentration of the initial number of atom at time zero. That is nt. So putting this formula 1/2 NO into time t, we will have it to be what? Ni is equals to n at time zero e exponential lambda t half. Are you seeing it now? Because we are talking about half of the number of atoms involved in the disintegration of radiations. So when you have it like this, you will now collect like terms. The next thing is to collect like terms. And how do you collect like terms? You collect like terms by dividing through by what? N0. All of them will be in the same place. So it will be 1/2 NO all over NO equals to what? E lambda TR. So remove exponential by introducing the natural logarithm ln. We remove exponential by introducing ln. Don't forget we said you need to know how to expand, and we said the first thing is to introduce integration, and that will remove what? The n. So if you introduce natural logarithm to both sides, to both sides of the reaction, to both sides of the formula, you have ni 1 all over 2 no over no equals to minus lambda t. Because if you introduce ni to this side, ni will cancel exponential, and it's gone. So now these are common things, you remove it. It will now be ni half equals to lambda t half. Remember, it's t half. Are you seeing it now? Ni half is equals to what? Minus 0.693 equals to minus lambda t half. That means half life, which is represented as t half, is equals to what? 0.693 over lambda decay. So that is it. That is the proof of half life. So with this, we have completed the topic of nuclear chemistry. So we will now take calculation on this. Calculation on these examples on nuclear chemistry. Calculation on nuclear chemistry. So let me read through the comments and see what we can. Okay, thank you. No, the environment is not dark, it's very bright. Go through your phone. Ensure that you increase the lightings of your phone, then you will see it better. Hmm? Increase the lighting. Yes, that is all for nuclear chemistry. Very easy, very understanding. Please, if you didn't participate from the beginning, go through the video and participate. So we will now take examples on their calculations from energy to to half life. So let's take this first example. Please, if you are ready to take the example, type ready. If you are ready to take the examples, type ready. We will soon end this session. My phone is going down. So if you are ready, please type ready. Type ready. I need more ready. I need more ready. We are waiting. We are waiting for more ready. Please, we are waiting for more ready. Okay. Esther, yes, ready. So Esther is ready, meaning everybody is ready. Joy has not typed ready. Joy, are you with us? Is Joy ready? Joy, we are waiting for you to tell us you are ready. Okay, thank you, Joy. Thank you,
All
Joy.
right.
So Grace is ready too. So I appreciate all of you that are present. So who else is not ready? I think everybody is ready. Good. Gary is ready. So let's take the example. Explain how is it related to the half-life. Okay, let's take the example. Explain the term radioactive decay constant. Explain the term radioactive decay constant. X. How is it related to the half-life period of a radioactive substance? How is it related? Is just this example, this proving that we did is is just the derivation we did that I just repeated. Explain the term radioactive decay constant S. How is it related to half-life period of this? So that is just the derivation. Now the question: the half-life of radium 228, the half-life of radium 228 is 16,020. The half-life of radium 228 is 1,620 years. The half-life of radium 228 is 1,620 years. Calculate the decay constant in unit of x, which is seconds, in unit of seconds. 2. Calculate the number of disintegration of calculate the number of disintegration calculate the number of disintegration of lambda 236 of radium 236. Calculate the number of disintegration of radium 236. Hope you have written that question. 2. Number 2 question. Number 2 question. A sample of radioactive material. A sample of radioactive material contains 10 raised to power 8 atoms. Contains 10 raised to power 8 atoms. A sample of radioactive material contains 10 raised to power 8 atoms. The half-life of the material is 2 days. The half-life of the material is 2 days. Calculate the fraction remaining after 5 days. Calculate the fraction remaining after 5 days. Then the activity of the sample after 5 days. Calculate the fraction remaining after 5 days and the activity of the sample remaining after 5 days. calculate the fraction remaining after 5 days and the activity of the sample after 5 days. So we will start with the last question that says a sample of radioactive material contains 10 raised to power 8 atoms. The half-life of the material is 2 days. Calculate the fraction remaining after 5 days and the activity of the sample after 5 days. So we'll take it one after the other. So from the question half-life, half-life is 2 days. Half-life is what? 2 days. Are you seeing it? Then the number of integration at time 0 is 10 raised to power 8 atoms. That is the number of atoms that disintegrates at the initial. They are now asking what is time t? What is the number of atoms after 5 days? The fraction remaining after 5 after 5 days. Fraction remaining after 5 days. That's what they are asking you. So the first thing is to calculate your lambda. Your lambda is your radioactive decay. Since they're giving you the half-life to be 2, so that means 0.693 divided by 2 will give us our lambda decay. Will give us our lambda decay. And that value, if you do your calculation, it is 0.3465. 0.3465. That is the value of lambda. Now, what will be time t after 5 days? That means the half-life is now 5 days. The time is now what? 5 days. So it will now be nt is equals to n0 exponential lambda t. So after 5 days is your t. Your lambda has already been calculated. You write the value of that one there. Then it will now be nt will be the fraction remaining times 10 raised to power 8 times e exponential. Your value of lambda is 0.3465 times what? 5. After 5 days, that is the time. So nt will be equals to 10 raised to power 8 e exponential minus what? Do 5 times that value, what do you have? 5 times the value, what do you have? Minus 1.7325. There will be 1.7325. So when you have done that, press your exponential raised to power minus this, multiply it by 10 raised to power 8. If you multiply that, what will be your value? Your value will be equal to 1.77 times 10 raised to power 7. 1.77 times 10 raised to power what? 7 atoms. That is the atoms remaining after 5 days. So the next question is, what is the activities after 5 days? Activity is equals to n naught over nt. Are you seeing it? N naught over what? Nt. So that means A is equals to what? 1.77 times 10 raised to power 7 all over 10 raised to power 8, which is equals to A is equals to what? So when you press your calculator, A will be equal to what? 0.178. A will be equal to 0.178. So that will be your activity. So your percentage activity, you just multiply by 1000, you get your percentage activity. So to the first question, hope you understand that. So I'm waiting for people to raise their calculator to get that.
Okay.
So that is that. For the first question about radio, hope we are there. First question about radio. Let me take the comment for this one we have solved and see. Let me take the comment. Uh, not I'm not seeing it clearly. Oh, Joanne has come. Oh, he said it's not clear. Okay, yes, Joanne, thank you. It's NT over N naught. Thank you. NT over N naught. Yes. You see when I did the calculation. Joanne, thank you so much for following up. Joanne, I will owe you a gift, or a Christmas gift. Joanne is the only one that is following up, giving me the correct said value. That's good. Okay, that means you are paying attention. That's good. Um, Usazua, what did you say? 0.346. Yes, correct. Multiply that by 5. Joy is asking where is E in the calculator. Okay. I'm not with your calculator now. I don't know where E is. I think E is second function of something. I'm not with your kind of calculator, so I don't know where exactly E is. In your phone calculator, E is just written there as E. But I don't know the calculator you are using, so I can't direct you. Sorry. No is 10 raised to power 8. Good. Marvelous. In the calculator there is E on it. Joanne said it is not clear. Hope it's not clear. Oh. It is not clear. Joanne, please let it be clear now. It's not clear. So Joanne, where are you confused? Where is it not clear? Okay, thank you for hugging us. um where are you not clear? Please let me know. Osezua said, ma, please, I think you made a mistake in the solution of activity. Yes, I corrected that. Thank you. Thank you. Activity is NT over NO. Activity is NT over NO. Thank you. Please, will you still take this in the class? No. Osage is asking if I will still take this in the class. No, ma, I won't take this in the class again. Oh, please, if you joined late, please, we will drop the live video. You can watch it again and again, and you will know it. Thank you. It's already there. Just watch from the beginning again. Okay, Raymond, yes, I've corrected that. Raymond, it's just the formula nt over n, but the value still remain. You know, the value we got after 5 days is 1.77, so it's still, the value still remains the same. Thank you. Joan, thank you. So we are going to the first question now. Thank you, Osage. So we are going to the first question. The first question talks about radium. What is the half-life decay constant in seconds? You know, half-life is measured in seconds. I said the time is measured in seconds. So it is the years that you convert. The first thing is to convert the years. They gave us the radian years to be 1620 years. They say we should calculate for. I hope I can clean the board now so that we can take the second question. They said the radian 228 has. Please, let's do the conversion. 1620 1620 years to seconds. Can someone do it for us? It is 1620 times 365 times 24 times 60 times 60. So when you have gotten the value, it means your half life is that value, and for your half life to be that value, impute the formula of decay constant equals to 0.693 over the half life. That will give us the amount in seconds. So I think we will stop here today, and we will continue. We have done with this topic finally, and I want to wish everyone happy resumption, and please prepare properly for your tests and exam, your forthcoming tests and exam. So we now have two major topics to take, which is acid and base, and also to finish up chemical equilibrium and electrochemistry. So thank you and God bless you. And I don't know if I'm still online now. Please, if you are with me, send a message, let me know that I'm still online. So am I with you? Are you with me? Are you still with me? But it's not. I don't know if so are we together? Are we okay? Okay, thank you. So yeah, I need response to the conversion of years to seconds. Have someone done the calculation? Let's see. What is your value? 1006 times 60 times 60. That is how to convert years to seconds. So press your calculator and let me know the value. Okay, so you will do that and paste it on the comment section. Paste it on the comment section after the live video. Thank you and God bless you. And I wish you success in all your endeavors. I pray that your watching this thing, this program, will not be in vain. And please keep on watching Chemtech Laboratory Tutorial. Keep sharing, keep liking, keep commenting. And God bless you. Bye.